Hello everyone, welcome back. I hope everyone's doing fine. So we've been progressing ahead in our econometrics series, and we are trying to we're trying to understand each and every aspect of econometrics that is relevant for our UGC NET exam. Okay, so whatever econometrics needs to be learned till your masters is being discussed here. Okay, so the last video was about your goodness of fit. Okay, and so let's move ahead from that. So today we'll be discussing a very small topic, and it's just a continuation of a topic that you have already uh, learned before, and it's a small topic. So the topic is basically a classical, sorry, let me im- change a bit of things here. So the topic is classical normal linear regression model. Okay, so we have already discussed your classical linear regression model. So the extra element here is of this word normal. So what this word means is, or what this addition means here is that it is basically talking about the normality condition. What is this condition? So let me just give you the idea. So it talks about normal distribution or distribution of your parameters being a normal distribution. And why this is important, why do we have to talk about the distribution of the parameters, or why we are talking about the normal distribution of parameters, we'll talk about that here. So since beta 1 hat, beta 2 hat and sigma hat square are random variables, we know that from our previous discussions that beta 1 hat, your beta 2 hat and sigma hat square are your random variables. Okay, because they can take any value, any random value. So that is why we need to formulate, or we need to find their probability distribution. So let's use the formula. Let's do this for beta 2 first, beta 2 hat. So we know that from our previous discussion that beta 2 hat is equal to your ki ui, summation of ki ui, where your ki is basically your small xi upon summation xi square. So we have already discussed this in our previous videos, how this came, and we know that yi is beta 1 plus beta 2 xi plus ui. Okay, so this implies beta 2 hat is summation of ki into beta 1 plus beta 2 xi plus ui. So I've just put this thing in place of yi. So in here we know that this is fixed, this is fixed, your xi's are fixed, your beta 2 is also fixed. Okay, all these values are almost your fixed values. Okay, we already know these values, and these values are taken as fixed values. The only variable that we have is this ui variable. So your beta 2 hat is a linear function, linear function of the random variable ui. Okay, which is we have assumed that it is a random variable when we had talked about the assumptions of our classical linear regression model. Okay, so this implies that the probability distribution of our beta 2 hat or beta 1 hat will depend on the assumption made about the probability distribution of ui. So whatever assumption I'm making about the distribution of ui variable, okay, that same distribution will be followed by my betas, okay, because my beta 2 hat and beta 1 hat are dependent upon ui itself because other values are fixed. Okay, so the classical normal linear regression model assumes that each ui is distributed normally, so that is why we get the term normal. So in here we assume that ui is normally distributed. So this is the graph of normal distribution. Okay, so the ui values follow this probability distribution function or this pattern. Okay, so expected value of ui is 0, we know this, and expected value of ui minus expected value of ui bracket whole square. Okay, so this is equal to expected value of ui square, which is equal to sigma square. So this is the variance of ui, and covariance between ui and uj is 0, and we know this from our previous discussions. Okay, so this implies that my ui variable follows normal distribution with mean as 0 and variance as sigma square. So this is the way we write a normal distribution. So my ui variable follows a normal distribution n with 0, the mean value being 0 and variance being sigma square. So this is the assumption about the ui variable in your classical normal linear regression model. Okay, so the question that might arise here is that why this assumption of normality? Okay, so there are a few things or a few reasons why we take this assumption. The first is your central limit theorem. So you must have read about this in your statistics classes. So it says that if there are a large number of independent and identically distributed random variables, then with a few exceptions, the distribution of their sum tends to be a normal distribution as the number of such variables go, increases indefinitely. So it basically means that if the number of UIs keeps on increasing and it becomes large and large, then the distribution of UI follows normal distribution. So this is a theorem in your statistics. So that is why the normality assumption is important. So as we take more and more samples and as we take more and more values of UI, the distribution of UI tends to move towards a normal distribution. And the second reason is that it comes from here only. Any linear function of a normally distributed variable is itself normally distributed. So I know that my beta 1 hat, beta 2 hat, and sigma square hat are all functions of ui. So if ui is normally distributed, it means that these values are, or these estimators are also normally distributed. Okay, and it is comparatively easy to deal with normal distributions because we have only two variables here, which is the mean and the variance. Okay, and it also allows us the normality condition or the normal distribution also allows us to use the TF and the chi-square statistical tools. So in between our analysis, we can also take the help of my TF and chi-square test or these statistics in the regression models. Because in a way these are somewhat substitutes or somewhat close substitutes of your normal distribution, and through these distribution we can reach the normal distribution also. Okay, so this was about the reason why we have chosen the normality condition in the classical linear regression model. Now let's talk about the properties of the OLS estimators under the normality assumption. So the first property is they are unbiased. So we know what this means because we have already discussed this in the classical linear regression model, and they have minimum variance, and together they uh, are called as efficient estimators, right? Now we have a third property. It's the consistency property. They have consistency. That is, as sample size increases, the estimators converge to the true population values. The value of estimator, the value of estimator becomes closer to the true population value. Okay. Another property is your beta 1 hat is normally distributed. Okay, with the your mean as beta 1 or the population parameter and variance as sigma square of beta 1. Similarly, your beta 2 hat is normally distributed with mean as beta 2 and your variance as sigma square beta 2. Okay, so you can also create a z statistics for these parameters. So it will be basically your minus beta 1 upon sigma beta 1 hat. Okay, so this is the z statistic, and this also follows the normal distribution. Okay, so you must have learned about the z statistic in your statistic classes, and it is basically a representation of how many standard deviations is our estimator away from the true parameter value, or my beta hat is away from the true beta 1 hat is away from my true beta 1 value. How many standard deviation it means we have to divide it by the uh, standard deviation of beta 1 itself. So z statistic measures that value, and it also follows a normal distribution. Okay, so you can also call beta 1 hat and beta 2 hat as best unbiased estimators. Okay, also also It allows us to use chi-square distribution. So n minus 2 sigma hat square upon sigma square is distributed as a chi-square distribution. Okay, with n minus 2 degrees of freedom. This knowledge allows us to draw inferences about the true sigma square from the estimated sigma square. Okay, so this knowledge of this following a chi-square distribution allows us to uh, make more inferences about or better inferences about the variance or the estimated variance, okay, through the estimated variance, sorry, of the true population variance through the estimated variance, right? So the normality condition or assumption enables us to derive the probability or sampling distribution of beta 1 hat, beta 2 hat, and sigma hat square. So this is the basic idea of this assumption, and this is what it helps in. And we'll see how uh, this normal distribution of our parameters is gonna help us to do the regression analysis in the upcoming videos. Okay, so we'll talk about regression in the next videos, and we'll talk about confidence intervals, we'll talk about significance test. Okay, so all these things will be covered in the next video. So I'll see you in the next video. Till then, take care.